All right, welcome to Physics 221, Chapter 33. So we're making a jump, right, all the way up to Chapter 33. So this chapter is about wave optics. Basically, interference of light, diffraction of light. So we're going to focus on light. That was a joke, focus on light. All right, anyway. So here's the objectives. We're going to introduce and use the wave model of light. We're going to understand how and why interference of light occurs. We'll understand the interference patterns of double slits, you already know that, and diffraction gratings, that's new. Study the inevitable spreading of waves due to diffraction. To look at how interferometers make controlled use of the interference of light to make measurements of the wavelength of light. All right, now, just pretend we're outside and it's dark. And I have a laser pointer and I shine it up at some star or something like that. What would it look like? I mean, you can see it for a while. Obviously, it's not going to travel all the way to the star, right? But you can see what's happening for a certain amount of distance. And what does it look like? It looks like a straight line, right? So you say, yeah, light travels in a straight line. So basically what we're saying is light, it acts like a ray. So you'd think that light's made up of particles or bullets, right? Travels in a straight line. On the other hand, I can do this. I can do it now, sorry. You see it? All right. Okay, so what was that? So all I did there is I had a laser pointer and I shined it through a really, really narrow slit. There's a piece of glass with black paper and I shined that laser pointer through a really, really narrow slit, a single slit. And what did we see? We saw some kind of a pattern. We saw that the light spread out. Well, what else spreads out after passing through a slit? You know the answer to that. We studied it last chapter, right? When you have waves going through a slit, they spread out. So, I just provided evidence that light also acts like a wave. So, sometimes it seems that light acts like a particle, sometimes light acts like a wave. This chapter is about the wave model of light. Next chapter is about the ray model of light. So we'll talk about lenses and mirrors and things like that. But this is all waves, okay? So wave model of light. Now, a little history. So Isaac Newton, who lived in late 1600s, early 1700s, he thought that light was made up of particles. Why? Well, because they didn't have the equipment to ever notice that when you pass light through a slit, it spread out. They didn't have laser pointers. They didn't have things like this. So they were never able to see any kind of diffraction. Now, Isaac Newton was the man back in those days. I mean, he was the world's best, most famous scientist. So if Isaac Newton said light was made out of particles, most people believed that, right? And again, there was no evidence to say otherwise. And so everybody pretty much thought that light acted like rays, particles. However, thank goodness, there are always some people that are willing to think differently in science. And there were a couple of people, Huygens and Hooke. They thought that light acted like waves. In fact, Huygens, he came up with something that we'll talk about a little bit later. He came up with a wave theory, which is based on Huygens' principle, which actually accounts for the refraction of light. Now, we haven't even talked about that yet, but you all know what it is. So imagine this is a swimming pool, let's say, and your leg's in the water. So let's say your leg is up to here in water. What does it look like? What does your leg look like? It looks like it's broken or something like that, right? Or it's bent. So that's refraction. So Huygens' wave theory was able to account for that. So all I'm saying is most people thought light was made out of particles, but a few people were working on the wave model of light. Now, there's another guy, Thomas Young, and he did the double slit experiment. And I already showed you this, so we're going to show it to you again. So this time, I'm going to shine the light through 2 slits. Hold on, as soon as I can find them. There they are. Right there. All right, so the light is going to go through 2 slits. There you go. Ah, come on. All right, thank you. Okay, so the light went through 2 slits. And again, if this is a screen, here's really thick metal or something. If light was made out of particles, you know, and it's going all crazy, you know, all this would get blocked, but the light would be able to go through the slit. You'd see one bright spot there, one bright spot there, if light was made out of particles. We didn't see that. We saw dark light, dark light, dark light. We saw an interference pattern, which is what we studied chapter 17. Ta-da! That's what we saw, right? So there it is, okay? So this is a photograph of an interference pattern from the this is called the double slit experiment. So you have a light source, and you're saying that the light acts like a wave, so the wave gets blocked except for the slits. Then you have the waves going through the slits, they interfere, and they produce this interference pattern. And where have you seen that before? Well, come on, we saw it last chapter, right? We accounted for everything, but we used water waves. We had the little pool of water with the little hammers, right? So it's exactly the same, right? Exactly the same. Okay, but now it's light. So, you know, we got to sort of start over. All right, that's not good. Don't ask me what I did, but anyway. Okay, so what we're going to do with light, we're going to use our wave theory of light, and we're going to do a couple of things. First of all, we're going to be able to figure out where the maxes and the mins are. All right, so we're going to do that. And then we're going to figure out the intensity. So you can see, you know, that the maximum intensity is here, then it kind of dies off, right? It's brightest here, and then it kind of dies off. So that's what we're going to do. So we're going to figure out the positions, and then the correct intensity. And it's going to take us a while, and we're going to learn a lot. All right? So that's what we're going to do. All right. Oh, yeah, that's what we saw with water waves. Exactly the same thing, right? Exactly the same thing. All right. All right, so here we go. Now, we're going to make some assumptions that are going to save us a lot of time and a lot of trouble. And the assumption is that the distance between the slits and the screen, this L, we're going to say that L is much, much larger than this. And I guarantee you it is. I mean, you know, when I did this, I mean, you can't see this, but the distance between the slits is, I don't know, like 1/10 of a millimeter or something like that. And obviously from me to the screen is a whole lot more than 1/10 of a millimeter. So this is an excellent approximation. So we're always going to assume that L, the distance from the slits to the screen, is tons bigger than this distance, which we're going to call D. But we're going to change that, don't worry. All right, D, okay? Now, what's the big deal about that? Well, if this is really, I mean, are these lines parallel? No. But I mean, if you move this screen way over, you know, like a mile away, what's it going to look like? It's going to look like these lines are parallel. So that's what we're going to do. Because L is tons bigger than this D, we're going to assume parallel rays. And that's a great assumption. And it's also correct. I mean, it's a correct assumption. We're not just being lazy. All right? Okay. Now, I should have told you this earlier. This chapter, there's not so much understanding, that sounds bad, as we had in chapter 17. There's mostly equations in this chapter. And so you have to understand the equations. If you don't, it's not going to make any sense. You're not going to know how to do your homework or the exam questions. So there's going to be times today where I'm going to have you stop the video and do a bunch of derivations. Please make sure you do them. If you don't do them, you're going to regret it. That's all I can say. All right? Okay, so here we go. So remember now, how did we get, we talked about interference last chapter. We talked about phase difference. We talked about path difference, right? Okay, so here's the question. What is the path difference between R1 and R2? Well, I mean, it's right here, right? So this is a right angle. So R1 travels this much more than R2. So that's the path difference, all right? That's the path difference. Okay, so we have to get an equation for the path difference. Now look, we know what d is, and we know what theta is. So what's that path difference? All right, so the path difference, we're going to call delta r, and just look at it, right? It's opposite to the angle, and that's the hypotenuse. So delta r is d sine theta. Okay, great. All right, so delta r is d sine theta. Now, we want to have constructive interference. Constructive interference. So therefore, just think back to the previous chapter, what do we want the path difference to be? Do we want it to be a half a wavelength, a full wavelength, 2 wavelengths? What? What do we want it to be? Well, I hope you remember, if the path difference is 1 wavelength or 2 wavelengths or 3 wavelengths, we'll get constructive interference. If it's a half a wavelength or 3 halves, we'll get destructive interference. So what I want constructive interference right now. So for constructive interference, we want delta r, which is d sine theta, to be equal to m lambda. And, as usual. Okay, so that's constructive. Okay, now, I just gave it away. What do we want the path length difference to be for destructive? Half a wavelength, 3 halves, and so forth, which is what we learned again last time. So for destructive interference, we want delta r, which is d sine theta, to be m plus a half lambda with the same m. All right, so that should make sense if you understood the previous chapter. Okay, now what we want to do is we want to find the positions on the screen where we have a max intensity and then a 0 intensity, so max and min. Now, in order to do this, we're going to use something called a small angle approximation. So here's a little trig for you. Okay, so remember from trig, tangent theta is sine theta divided by cos theta. Now, what's cosine of a really, really small angle? It's like 1. So therefore, this is approximately equal to sine theta. Okay? So that's one. There's more than one small angle approximation, but this is one of them. So tangent theta is approximately equal to sine theta for small angles. Small angles. Right? It's what's called a small angle approximation. Now, everybody, whenever I say that, they say, what's small, right? So here, and of course, theta has to be in radians. Okay, so I have it in degrees and in radians, but whatever. I mean, it's both, right? Doesn't matter. Okay, so let's see. So here's theta in degrees, here's theta in radians. Okay, so look at, so theta, sine theta. So look at, it's exactly the same, right? And here's tangent, right? So we're saying that tangent equals sine. So tangent equals sine. Now that's, that's 0.1 radians, which is like 6 degrees. Okay, then we go like 0.2 radians, 11.5 degrees. 0.199, 0.203, pretty close, right? Sine is equal to tangent, close. 17 degrees, still pretty close. 23 degrees. I mean, we're getting a little bit further away, but come on, it's pretty good, right? It's pretty good for, 20 degrees and less. And it obviously gets really bad later on, right? Okay, so this is approximately equal to that. All right, now's the time where you guys have to do the work. And make sure you do it. Okay, so what I want you to do now, I wish we were in a class, because that would take, I don't care how long, but you need to know how to do this. It's super important. So what you want to figure out is this distance, ym, this distance, in terms of m, l, lambda, and d. You hear that? So the military is doing a flyby at various places around the island today, and they say that the whole purpose is to honor the healthcare providers, the first responders. So pretty loud if we could hear it in here. All right, so use everything up here. Use this. And figure out what ym is. So stop your video and figure it out. All right, so we're back. I assume you did it. Okay, so what do we know? Or what do we want to know? We want to know this, and we already know this is L. So what angle is that? It's tangent, right? All right, so we're going to say ym, so ym equals L tan theta. Okay, that makes sense. But now, small angle approximation. And you can see why we want small angle approximation, right? Because we want to use this, Okay, so let's see, L tan theta, so that's the same thing as L sine theta. And we're finding ym for constructive. We want to know where the maxes are. So then, let's see, where's sine theta for constructive? Right here. Right? So this says that sine theta equals m lambda over d. So we'll just substitute it. So sine theta, so we have m lambda L over d. Which, if we're cool, which we are, we can write as m lambda L over d. Because remember, m is an index. So it's kind of nice to have the index outside. Okay? All right. So there it is. Ym equals m lambda L over d. All right? Now, everyone, please figure out ym for destructive interference. So pause your video and do it, please. All right, we're back. All right, it's very similar. So again, we know L, and we're trying to find y. So we're going to use tangent. All right, so ym equals L tan theta. But tangent theta equals sine theta, or close enough. So we have L sine theta. But now it's destructive interference. So we're going to use this. So therefore, sine theta equals m plus a half lambda over d. So now we plug it in. So we get m plus a half, bring it outside. Then you're going to have lambda L over D. There you go. So there it is. And hopefully you were able to do that. Right? So constructive, just m times this. Destructive, m plus a half times that. All right, one more thing. So now, so we have where the maxes are, we have the mins are. So now please figure out the distance, delta y, from a max to a max, or, same thing, right, min to min. So use these equations and figure out delta y, max to max, or min to min. So pause your video and figure that out, please. Okay, we're back, and you should be able to figure this out, right? So y1 equals L lambda over D, y2 equals 2 L lambda over D, y3 equals 3 L lambda over D. So what's delta y? Just lambda L over D, right? So delta y is just L lambda over D. And you know, you could have done it with this too, right? You could have said, you know, start off with y1, 3 halves L lambda over D, y2, 5 halves L lambda over D, then subtract them, and you're just going to get L lambda over D. So you make sure you know how to get all of these equations, because we're going to use them, all right? We're going to use them. Now, here's the awesome part. These equations that we just derived, so this here tells you where the maxes are, tells you where the mins are, tells you the distance between them. They agree exactly with the data. So that's good, right? That means our wave theory of light is working, all right? It works. It's awesome. Now, let me just say, you know, in the real world, if we were doing this experiment, I mean, it's a piece of cake to measure L and to measure D and to measure the y's, you know? And so, you know, you can use these equations to figure out the wavelength of light. Now, I hope you realize that's incredibly impressive. I mean, the wavelength of light is between 4 and 7 times 10 to the minus 7 meters. I mean, that is incredibly small, right? You know, like 5 times 10 to the minus 7 meters, that's incredibly small. And we can just figure it out just doing that double slit experiment. So that's incredible. That's totally incredible. All right, let's quit now.